So today's lecture is about pointers and how memory is arranged inside of a program. This is historically one of the most difficult concepts in this class. So warning signs, please pay a little bit extra attention than usual. If you would like, there's this fun little write-up that's really helpful from Stanford. If you read the first section of this, if not the whole thing, it will be very helpful. Okay? Lots of diagrams like the kinds that I'm going to be showing you today. Okay? So that is hopefully something that will be helpful to you. But yeah, we're going to learn how memory works. So we've just been interacting with it. I've been drawing boxes for you. That's not really what's going on inside the computer, right? The computer's not making a box. What is it really doing? So we're going to figure that out today. All right? So the question is, why learn this concept called pointers? Why care about how memory is arranged in our program? If nothing else, it's going to be able to laugh at this joke by the end of these slides. But in reality, it's going to be really nice to learn how memory is arranged because it's going to make you more aware of how your program's running, and therefore you'll be able to make faster programs. You'll be able to understand errors a bit more clearly now, like some weird errors that are getting output when bad things happen, like you access a weird index of an array and then something goes wrong and it says like segmentation fault. What does that even mean? So that all has to do with memory and this concept called pointers. And that will shed light on all the issues that you have been having and that you will have, all right? And you'll become a better programmer because of it. So that's my motivation for you. So yeah, let's learn about what memory actually looks like under the hood when we run our programs. What does memory actually look like? And when I say memory, that just means like RAM. If you've heard of that, random access memory. That's the memory inside of your computer that all your programs, remember, they get copied into RAM before they get run. That's how it all works. So yeah, let's learn what it looks like, really. Okay, so your computer's memory, it's not like int x equals 42, you make a box called x. It's just a giant table. It's a giant lookup table. That's what your memory is, really. So here's what memory looks like. Here's the new drawing. It's a giant table that maps things called addresses, which are places to hold stuff. Addresses can be large. They get to be up to 64-bit numbers with a 64-bit processor like the ones that we all use today. And each address maps to a single byte value. All right? So every address in memory is just a big table starting at address 0, of course. You can map to an 8-bit value. All right? So at address 0, you can put the 8-bit number 42. At address 1, you can put the 8-bit number 43. Okay? And so on and so forth. And it just continues. Address 2, address 3, so on and so forth, for as much memory as you have in your program. Or how much memory you have inside of your computer. So yeah, you can store, 87 at address 2, 88 at address 3, and then you can change stuff. You can say, hey memory, please go to address 2 and change whatever is there to one more than what used to be there. So make it 88. Change at address 3 to the byte value that's the biggest one possible. That's 255. That's as big as it can go, okay? So yeah, that's how you manipulate your memory. Everything is mapped from an address. An address takes you to a single byte value, and if you have like 4 gigabytes of memory, you have essentially 4 billion value slots. And you have to have 4 billion addresses then as well. Okay? That's the idea. So an address is just the place where that byte lives. It's like its little mailbox. It's its house. So address 2, the memory knows to go exactly there and change the byte there or get the value. Okay? You can send data to an address or look up the data that's there, like print out the 43 or change the 87 to the 88, stuff like that. Okay? That is the idea. And then every time you make a variable in your program, it's not making a box of memory, it's just taking up some addresses. That's all that's really happening, right? Every variable, piece of data, including your code as well, it's stored in memory at a certain address, okay? Usually you care most about if things are like long, they're made up of multiple bytes, you care about the starting address, where that data lives/begins, okay? But if it's a single byte like a char, that's just its address is where it is. Okay? Any questions about that? That is what memory really is like. Just a big lookup table. Addresses to values, byte values. Your next question is probably, okay, int x equals 42. How do I store an int then? Ints are 4 bytes. Doubles are 8 bytes. How do I store those things? Every address holds a single byte. How do I put an int in memory? They take up 4 contiguous bytes. That's how it works. And they're referenced by a starting address. So int x equals 42. It's being placed in memory. Again, you have your addresses and your values. Boop, 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 boop. Let's say that the x variable, like I'll draw it like this. Let's say that its starting address is address 16. So instead of x, I'll say 16 up there. So 16 is where it begins. And if it takes up 4 bytes, it'll take up addresses 16, 17, 18, and 19. Just to store that one int. All right? And so somehow, across all of those 4 bytes, and I forgot a line, across those 4 bytes, 42 is in there. It's just make the binary number 42 and put a bunch of zeros at the front, essentially. So that's what's going on in memory. If x lives at address 16, holding 42, starting at address 16, you use up the 4 bytes from there on. 16, 17, 18, and 19. That is where x starts. Where the int x starts. So it's always about the starting address if it's a multi-byte thing. Okay? And if you want to store other stuff in your program, you find new addresses for them. So like if you want to store a string of characters, maybe you have a starting address and it stores like hello. You store the H, the E, those are each 1 byte, L, O, all that stuff. It's somewhere else in memory. Dot, 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 dot. All right? That's the idea. We can always make a number out of everything. Everything is ones and zeros at the end of the day, right? So like doubles, for example, they're going to take up 8 bytes. 8 addresses. Strings, they're made up of characters, and characters are just ASCII valued bytes. Like the character H was a certain number, right? You remember that? So yeah, they all live next to each other in memory, starting at a starting address. Am I still good with that? Any questions about this concept? Again, this is a harder concept. How do you store non-numbers? How do you store bigger stuff? Okay. If we're still doing fine, let me teach you some new kind of base. All right. So we like to use binary, of course. We think about things in binary. Everything inside of a computer is binary encoded, but it's hard to look at a bunch of ones and zeros and understand what's actually going on. So we use base 16 instead when we print stuff out. Usually that's binary valued. So I'm going to teach you base 16. It's also called hexadecimal. That's its fancy name. Hexa for 6 and deci for 10, so 16, base 16. It's called hex for short, and C++ likes to print out addresses in hex, because otherwise it would take up 64 ones and zeros. That would be ugly. So hex is base 16. It plays really nicely with binary because it's a base that is a power of 2. But remember, like decimal is base 10. We have 10 digits, 0 through 9, right? Hexadecimal is base 16. We need 16 digits. Ooh. So that means you have 0 through 9, but then you need a single digit to represent 10. Does that make sense? So we just use letters. 10 is A, 11 is B, 12 is C, D is 13, E is 14, and F is 15. So now we have 16 digits. If I try to add one more, F base 16 plus 1 base 16, that is when we finally carry and make 1 0 base 16. That'll be our number 16. Okay, any questions about that? That's a bit weird. Yeah, Yeah, and so it's a lot easier to store or to print out binary information in hex, because instead of printing like a byte that is like this binary number, this will actually translate into 2 hex digits. So it's a big space savings in terms of output. Every 2 hex digits, that corresponds exactly to 1 byte of information. So every digit in hex is 4 bits. It represents 4 bits. It has 16 things. 2, 4, 8, 16 to the 4th is 16. That's how that works out. The terminal can't do subscripts, and so if it wants to show you a hex number and make you know that it was a hexadecimal number and not a binary number, or not a decimal number, because you can have the same thing, like 77 in base 16, that's not 77, right? You can have things that look the same, so we have to specify that it really is base 16. So the computer will print out it with a 0x at the front, just to indicate that the number following the 0 and the x is a hexadecimal number. Okay? So 0x3a is shorthand for 3a base 16. And let's discover what 0x3a is in decimal. What number is this really in our normal number system? So again, you just use our base conversion. So this is times 16 to the 0. This is times 16 to the 1, that place. So this is a times 16 to the 0, and then plus the 3. 3 times 16 to the 1, which is equal to 3 times 16 plus 16 to the 0 is 1. What is a, though? A is 10. 3 times 16 plus 10, which is apparently 58. I did the math ahead of time. So 3a in hex is 58 in decimal. That's a new number system, and it's super helpful because like the smallest byte is 00, 2 hex digits, and then FF is the largest byte, that's 255. Every 2 hexadecimal digits corresponds exactly to 1 byte, so that's why it's fun to print out. If you want to print out a 64-bit address, you only need, what is it? 16? Yeah, 16 hex digits. Divide by 4. All right, are we good with this new number system? It's a bit weird, but that is going to allow us to print out things and manipulate addresses. Now you won't be scared by the zeros and the x's and the letters inside of numbers. All right, so yeah, here's some examples. It's time for examples, that's for sure. How do I want to do this? I don't think I even want code yet, actually. So let me just draw what's going to happen here. So int x, int y, int z equals y, all these things. So these lines before, this is how I drew that for you, right? X is a box holding 42, y is a box holding 43, and then z is a brand new box holding whatever y held, so that's 43 as well. Okay? But in reality, those lines, yes, they make boxes in memory, but they're all going inside of that table, that address value table. These are new things that we now care about. First of all, we need to understand that they're all separate places in memory. They're all separate boxes. That's important, which means that they all live in different places in memory. They all have a different starting address, right? So maybe X lives at address 4. Y, it takes up 4, 5, 6, and 7, right? So maybe if Y wanted to come next, it needs to start at address 8. It can't like clobber pieces of X. And then if Z wants to come right after that, it would have to start at address 12, right? Assuming decimal addresses. All right. And actually, these two bullets mean the same thing. Separate boxes, separate memory addresses. Those go hand in hand. So yeah, this is what's going on in the address value table. Let me go back to blue. So ... X takes up addresses 4, 5, 6, and 7. That's where X begins. Y takes up addresses, they're ints, right? 8, 9, 10, and 11. That's where Y begins. And then Z will take up addresses 12, 13, 14, and 15. That's where Z begins, ... Anything else can come after. more pieces of memory. And so for those 4 bytes, somehow it's encoding the number 42 for X. For these 4 bytes, starting where Y lives, those encode 43 somehow, and then the final 4 bytes for Z also encode 43. Same number, different place in memory though. Okay? And so yeah, the computer knows nothing about variable names. Once it gets compiled and it gets run, it just knows that all these things live at a place in memory. It knows how to get to there. So humans use variable names. Computers, they're just thinking of like, oh, okay, box called 4, box called 8, box called 12. That's what's going on inside the computer. And yeah, separate boxes, different memory addresses. Those correspond 1 to 1. Are there any questions about this idea? Just, again, trying to get you used to this idea of addresses. Everything in your program lives somewhere. It has a starting address. It takes up a certain number of bytes after that address, potentially. Oops. All right, if we're good with this, I have kind of a review question for you, actually. So let's pretend like we're writing a program and there's like a character or something and it's that character's birthday. And so we make a birthday function. Like age was 19, print it out. We call birthday on age and then we print it out again. That makes, we set a equal to a plus 1. What does this print? I'll give you like 2 minutes to think about this and remember. Go to the ByClicker page, please, and enter in your answer as a group. Yeah, see if you remember what's going on here. What is it going to print? Or is it going to be an error? How long did I say? I'll give you 2 minutes, let's say. Convince your neighbors that you are correct. "30 more seconds. All right. So let's see what we were thinking. Boop. Yay, good. So this is supposed to be a review. I'm glad that we all are mostly agreeing. The answer is, in fact, A. And can anybody tell me why? Like, what's the reason? That's, I guess, part of the reason. There's like a disconnect between this function and this function. Do you have another explanation? That's right. There's no link between A and age. And the fancy term is we called this function, this int is taken by value. Remember call by value versus call by reference? This is called by value. We're just copying into a brand new place in memory, a brand new box, A. Okay? So that's why it's going to print 1919. We're going to jump up here, call birthday with age. A is going to get set to age. A equals A plus 1. That's going to manipulate A, but that's a brand new variable. It's a separate variable local to the birthday function. Okay? It won't change age at all. If we zoom in, here's what happens, right? Main has an age variable, and that's set to 19, right? And then we pass it along to the birthday function, which itself has this parameter, which is passed by value. It's just an integer. It's local to birthday. So it has its own A, and it's set to the same as age, 19. And then it does A equals A plus 1, right? That will change A to 20, but it does nothing to age, right? They're different places in memory. You can think of them as having different addresses. That's exactly what's going to happen, in fact. That's what it means to be a different variable, a different place in memory. Okay? And so when this returns, we're back in main and nothing happened, right? Any questions about that? Does that make sense still? Okay, so that's called by value. That is, we passed to a parameter that we passed a value as an argument to this parameter it is its own variable, brand new place in memory. Okay, if we really wanted age in main to change, we could have used references. We know how to do that, right? References, though, are secretly using a concept called pointers, messing with address stuff, doing it for you. So let me teach you how to manipulate values using addresses, holding on to addresses and following them and working with pointers. Okay? So that's where we're going. So here is what a pointer is. A pointer is just a fancy word for a variable that holds, not like a double and into char, it's a variable that holds a memory address. You can hold on to somebody else's memory address. Okay? A pointer is a variable that holds the address of another variable. And we say then that once we have that variable holding the address of another variable, it points to it. It points to that variable that it has the address of, that it knows the address of. Okay? That's how it works. And this is how you create a pointer variable. You give it a name, just like usual. If you want it to point to an int, though, you have to say int here. And then there's an extra star, just like there was an ampersand with references. Now there's a star for pointers. So it might be like int star pointer, int star p, double star p. All right? And again, the white space doesn't matter. You can put the star anywhere. I'm going to put it closer to the type than the variable name, but C++ doesn't care. So yeah, pointers, they are type specific. If you want to hold the address of an int, you have to say int star. It's kind of backwards. You read it like p is a pointer to an int. You read it backwards like that. P is a pointer. The star kind of means pointer to an int. Okay. So this line is going to make a box in memory, but it's going to hold garbage as usual. But this box is special in that it can hold the address of another variable. It can remember where that other variable lives. P itself, being a variable, it also has an address. It lives at address 100 or something, but we just don't care about that. You might care about it later. Okay? If you are not ready, if you don't have an int ready to like set P into, or set into P, if you don't have an address to give to P yet, because it's supposed to hold on to int addresses, then you can give it a special unused address that is always like not used. It's address 0. Secretly, address 0 cannot hold anything. It's meant to mark that there's nothing there. So null pointer, nullptr, I'll just say null for short. That's a special address. It's the 0 address. No program can use the 0 address. It is reserved just to mark that nothing's there. Okay? That's how you do it. Are there any questions about that? So this is a new kind of type, int star. Think of it as one big type. P is a pointer to an int. This can eventually hold either null or the address of a variable that is an integer. Crazy. Are we ready to give P an int to hold on to, an int address to hold on to? All right, let's do it. So Let me make sure. Am I happy with this yet? So, okay. Let's make an integer and a pointer to an integer, right? Let's figure out what's going on in memory. So here is int x equals 5. That makes this box, right? Called x to us, but to the computer it lives at some address. Let's say it's address 100 in hex this time. And it's going to hold 5 in its 4 bytes. And then we're going to make int star p. That is a variable. Of course, it has its own address, but it's capable of holding an int address. So we'd like to have it hold the address of x, right? The address of x is 100. We'd like to put 100 into p. Does that make sense? And then it's like it points to it. That's how I'll draw that in a second. Okay? But yeah, let's just get started with that. Let me show you this in code for now. Pointers.cpp. So I made int x equals 5, and then I'll make int star p. And right now p is set to garbage. It holds a garbage not number, it holds a garbage address. Right? Just like double D semicolon would hold a garbage double value. This holds a garbage address value. That's what it's supposed to hold on to. P is a pointer to an int. It can hold addresses of ints. Okay? So let's see out P. Because P holds addresses. It's set to some garbage address right now, but let me show you what it looks like when it prints out an address in C++. We were very lucky, it seems. It was set to null for us. That's pretty nice. You can't guarantee that, though. This is supposed to be a garbage address. It could be anything. It could be anything in memory. And if I run this program enough times to fill up the memory of this virtual computer, it will start giving me random stuff. But for now, it's happy. Maybe if I mess with it and make like a giant array or something, it will give me a garbage address this time. Yeah, no. I'd have to play with it. I'd have to keep this computer on for longer, maybe. So yeah, that's a pointer, and it prints out an address. 0 means the address. It's supposed to be null. Okay. Question? Yeah. It's the address of nothing right now because it's not pointing to anything yet. It's just a garbage address. It's not hooked up yet, and so you shouldn't use P. You should not use P right now. It's not ready. Actually, just to prove to you that this really is garbage, let me go to a computer that has been on for a few months, our class server. Whee. Yeah, too many random programs here, but let's try compiling and running it here, just for fun. There. Much better. So this is a garbage address, and it'll be different every time. Boop, boop, boop. It's just whatever is in memory. It interprets it as an address, which is printed out as hex. That's fun. Okay, so back to this. We still good with this idea? P is a pointer to an int. It can hold the address of an int variable. So we'd like to give it the address of x eventually, whatever that might be. All right? So let's initialize P to a value. All right? And this is where I tell you, this is where I apologize to you for the makers of C++ and C, because they're using the ampersand. This ampersand, we already know it can mean reference if it's used in a type. If it's used outside of a type, like on the right-hand side of an equality, it means a completely different thing that has to do with pointers. I'm very sorry. It also means a completely different third thing that we'll learn about at the end of the class. It's a bitwise AND operator. So that sucks, but you'll get used to it. So the operator ampersand used outside of a type, it's like you put it next to a variable name. That gets you the address of that variable. It's called the address of operator. Okay? So it returns, essentially, it gives you back the address of the variable that you place after it. So this taken together will get replaced with, it means address of x. Okay? And so that will set this up. If I say P equals address of x, it will figure out the address of x, not the value, but the address, and it will store that into P. So it'll put 100 into P. And that means P points to x now, because it holds its address. And so we draw an arrow like this, from the middle of P, because it's holding on to the address, to like the outer edge of the x, because that's where it knows how to get to now. If only we could move along this arrow. Okay? So we've set it up like this. P is pointing to x, and that's the diagram. Does that make sense? Any questions about that? So yeah, by default, if you don't have a place to like hook P into yet, then set P to null. That's a special address. Null pointer is a special unused address. It's the 0 address is unused always. Cout P. Again, on this computer, it'll print 0, 0 twice, but really it'll print a garbage value, then 0. That's what it's supposed to do. This is garbage. We have no control over it, and then this one is always going to be 0 because we set it to null. Okay? So that's how that one works. That's how null works. But now we have a place. We have a value to give into P. We can initialize P now. P equals the address of x. Okay? And now if I print P, it's going to be wherever x was made in memory. And that's going to be different every time the program runs. That's for sure. So this is apparently the address of x for this run of the program. This is apparently the address of x for this run of the program. And so on and so forth. Keep on running it, you keep on getting a new address. Because the program gets loaded into a different place in memory each time. It's all non-deterministic. Any questions about that? So P is now holding on to the address of x, and it's this fancy number. The reason pointers are at all useful is because you are able to follow them. You're able to move along this arrow and get to this place in memory and look at the 5 through P without ever mentioning the word x. That's what pointers can do for you. Okay? That's where we're going. So yeah, let's use P. All right? Actually, let me introduce this to you in a question form. It's the star operator. Again, overloaded, I'm so sorry. So the star operator in a type means pointer. The star operator outside of a type, next to the name of a pointer, like star P here, that follows the pointer. Okay, it's called the dereference operator. It follows the pointer to the right of it. So what do you think this code is going to print then? I'll give you like a minute, because I think I gave you a big hint. But if this is all set up like this, and I say cout star P, and it's supposed to dereference, that's the fancy word for follow, it's supposed to follow P, what do you think it's going to print? Will it print 104, 5, 100? Which one? So try that. I'll give you a minute to think about it and discuss. And please enter in your answer. It's meant to follow the pointer. How would we like it to follow? I haven't told you exactly what it's going to do. What do you think it should do? Give me another 20 seconds. So x lives at address 100, it holds 5. P lives at address 104, it holds 100, or 100 if this is hex, and it's able to remember where x lives. Right? So what do we think star P should print? We are not at all sure. So let's think about this. How can I get it to print 100? I just did that. It would have been cout what? Just P. So it would be useless for this to print 100, right? Completely useless. How could I get it to print 104? Because the answer is B. What is 104? What does that mean in terms of P? Yeah, it's the address of P. So if I wanted that, it would be ampersand P. Does that make sense? So that's another way to get that. It's useless for that to be what star P should do. So the answer is going to be B. It's going to follow the pointer, get to the value there at that address, and retrieve it or change it. So the answer is the one we thought it wasn't. B. Okay? Let me show that to you. Because the other ones are taken care of. There's another way to get to all of those things through P. Star P, the one thing that you can't get without this operator is the value of what's being pointed to. There's the 5. Okay, so star P is going to give us 5. It's as if we said C out X. Star P is equivalent to X at this point. Okay? Does that make sense? So anywhere you could have used X, you can now say star P. And that allows me to use this pointer to manipulate somebody else's value. This is sounding a whole lot like references, isn't it? This is what references are doing under the hood for you. They're setting up pointers and dereferencing them. Okay? And that is the goal. So yeah, this is what pointers allow you to do, this idea of indirection. Dereferencing a pointer gets you to the value of the thing it's pointing to. Right? That's called the pointee, the thing being pointed to. And so it gets you the contents of the box, let's say. So if this was X, it held 5, it lived at address 100 really, and this is P, it lives at address 104, not that we care, it holds 100, and that means it's pointing to the X variable. It holds its starting address, all right? Pointers allow you to both access and modify another variable. So I could have said star P equals 6. That would have been equivalent to the line X equals 6. So it really is the same. Star P really is X at this point. That will set this to 6 after that line, right? And then this line should make a lot of sense. This is equivalent to X equals X plus 1. First you do the right side. It's like go to P, dereference it, get the value there. That's 6. Make 7. Store that back into wherever P is pointing to. Store that back here. So store 7 back to where it came. Add 1. So that'll make 7 there. Does that make sense to us? It's essentially references all over again, just with an extra step. So star P equals star P plus 1. See out, I can see out X, right? Because I really am changing X through P. This is the variable that's really being changed, X. And then star P means the same thing, because it's holding the address, and it's going to that address's place in memory. Getting the value back, changing the value. And so these last two are going to both say 6, because X is star P. Star P goes to the value that it's pointing to. X is that value. Get its contents. Get its contents. So 2 6s. Any questions? We still good with that? Again, this is one of the harder concepts, I would say. So now we have a second way, besides call by reference, to fix that birthday problem. All right? Now we can do this. Instead of passing a copy of an int or a reference to an int, which is just a new name for the same thing, we can pass the address of an integer. We can take an address, okay? So make our age, print it out, 19, and call birthday with the address of our age variable. We're giving birthday the address of our own variable. And of course, it's able to modify it by following that pointer through that address. You see that? That's the goal. Then we jump up here with A set to the address of age, which let's pretend is 100. So A is set to 100. Then I do star equals star A plus 1. It follows the pointer and messes with this memory. Sets it to 20. Does that make sense? So that's secretly what references are doing for you. They're like, it's secretly passing along the address and secretly dereferencing everything everywhere. This is what's really happening. Okay? We good with that? Let me just prove to you. Let me put this in our code from class so that you can see it forever. This is called call by, not reference, it's called call by address or call by pointer. Call by adder or something. Let's do that. Oops, not like that. And of course, I have weird space characters by pasting from PowerPoint. There we go. And so this really is going to print 1920. Cool. Because star A, int star A, is really, I guess I want to draw it like this. Star A. You put it over there too. That's equal to, going to be set to the address of age. That's what I'm calling it with. And so it'll be able to dereference, go to the address, which is mess with the age variable for real. Make it 20. Okay? So that's how I can modify somebody else's variable if I pass along the address. That's another way to get to it. All right. Let's see here. I have a very interesting idea for you next. What question first? That's right. This will compute the address of the age variable. On this line, it's dereferencing the A variable. A is a pointer to an int. The asterisk in the type means it's a pointer to an int. And then here in the use, and star A means follow the pointer. Follow the pointer, get to the value that it's pointing to. And either change it if it's on the left side of an equal sign, or just get the value if it's on the right side. Does that make more sense? It's definitely going to take a little while to sink in, that's for sure. Any other questions? All right, so let's go deeper. Here is a pointer diagram, right? So I've got some pointers, they're pointing to some values. Let's say that the original variable is x, x is an int. I can have, it's not a problem to have a pointer to an int, right? Pointer to an int, but this is a pointer to a pointer. You see that? That's not a problem. So given this kind of diagram, I might ask you one day to show all the different ways that you could change x, like make it 6 or something. You can, of course, say x equals 6, but what else can you do? You have p, right? P is a pointer to x. It holds the address of x. So I could say star p equals 6 too, right? Star p equals 6. That would also set x to 6. Yes? That would set this variable. I could also use q, right? Q is kind of the same as p. It's both, they're also holding 100. So I could say star q equals 6. That would also change this box to 6. Any one of these are valid. Does anybody have a guess of how to use R to make x 6? That's close. If I said star R equals 6, what is R pointing to? Address 150. That's Q, right? So it would change this to 6. That's not far enough. But if star R gives you Q, how do you get from Q to X? One more star, right? Okay. Star R equals 6. That works. That'll do it. Are there any questions about that? That's weird, right? 1 star R gets to address 150 and it's talking about this. It gets the value, retrieves it, changes it. Now we're here at this place. If we dereference that, that just goes to address 100. So that brings us here. A second dereference. That's not a problem. You can have pointers to pointers. With that in mind, if I give you the same diagram, what are the types of these variables? Or x is an int, of course. This is the syntax for that. If you get to a fancy programming languages class one day, you put a colon after the name of a variable to say what type it is. So x's type is an int. You would declare it like this, int x. Right? How would you have declared p or q? What's their type have to be? That's right, it would have been int star p. Int star p and int star q. Because they're pointers to ints. They hold the address of x, which is an int, right? Int star q. And that's because, so p is an int star, q is an int star. And that's because if you take the address of x, that's not an int anymore, it's the address of an int. Ampersand x makes an int star, doesn't it? That's the type of this expression. So that if I want to hold on to the address of x, I better have an int star. I need to save the address. I need a pointer to an integer. Okay? So essentially the ampersand adds a star. It gives you the address of the int. Does that make sense? So int star p, int star q. All right. R is pointing to q, which is an int star. So if I get the address of q, I need to move this up. If I ask C++ for the address of q, what is the type of that expression? Address of q, please. Can you follow this pattern? Do you see it? It'll be int star star. So if this was an int, I added an ampersand, got the address of it. That was the address of an int. So I got a pointer to an int. You read it kind of backwards. If I am starting with an int star, and I'm asking for a pointer to that, that is, all right, here's the original type. I'm getting a pointer to that, so I'm getting an address of an int star. An int star star. Does that make sense to us? So R must be int star star R. That's how it must have been declared. It's a pointer to an int star. You can separate it like that and read it like that. Just like P and Q are pointers to just an int. We're going to hold the address of an int. R is going to hold the address of an int star, so it's going to be a pointer to an int star star total. We can keep going, right? We can say Z holds address 250 as its value, and so it points to R. This would be then, Z would have to be of type int star star star, wouldn't it? Because it's a pointer to an int star star. You can have as many as you want. Not a problem. Int star 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 Z. Are we still okay with that? That's a lot. Okay, let's do it. Back to our pointers program. Whee. I'll just put a new line for our new stuff here. So x still holds 5 up here, right? Or maybe it holds 6 now, sorry. And we have p already. P has been set to be the address of x. Let's make q, and let's make r, and let's make z. So int star q holds the address of x just like p did. Int star q is its type, and it's going to hold the address of x, which is the 100. Okay, that's fine. Int star star r needs to hold the address of q, the 150, right? That needs to go in here. So int star star r equals the address of q. Yeah? Int star 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 z will hold the address of r. That's the 250. You can do that all day long if you want. So now I have so many different ways to print out x, to get to x, and to change it or retrieve its value. I could see out x. I could see out star p, right? All these different ways that we were talking about over here. I could see out star p. I could see out star q. I could see out star star r, right? Follow r to get to q, then follow q to get to x. And then I can do int or star 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 z. follow Z to get to R, follow R to get to Q, follow Q to get to X. So there's a nice one-to-one correspondence between the number of arrows that you want to follow and the number of stars that you write in your code. If I want to get to X, I have to follow 3 arrows from Z. That's 3 stars. 1 star, 2 star, 3 stars. That's one way to think about it. Alternatively, like the types are telling you, like, if you're at R, you need to dereference twice, 2 stars to get to an int. 1 star, 2 star. That gets you the final int. That's another way to think about it. But yeah, all of these lines are going to print, I think, 6. Yay. So many different ways to print 6 now. Are there any questions about that? You can hold the addresses of things. You can hold the addresses of other things that are themselves things that hold addresses. Have pointers to pointers. Not a problem. So yeah, this is probably a little terrifying. Are we still okay? Okay, let's keep going then. We're almost done for the day at least. Let's talk about segmentation faults now. Seg faults for short. So yeah, there's a bunch of different ways to get a seg fault, but the main reason is if you've never had your program stop and it says segmentation fault as the error output, it's a runtime error. The reason that is happening is you're trying to access memory that isn't yours, or you're trying to dereference the null address, which is 0. That doesn't belong to anybody. So if you do that, you get a segmentation fault. That's a seg fault for short. It's a runtime error. You cannot recover from it. You messed up if you tried to access memory that wasn't yours. So either you try to go past the amount of memory that your program has been allocated by the operating system. So your program only gets so much memory assigned to it. You can't like ask for if you have a 4 GB memory inside of your computer, you can't ask for the address that would have been that's really, really high, that would have only been there if you had 8 GB of memory or something. That just doesn't exist to you. And you really don't get all of your memory as well because you have all these other programs sharing your memory, right? Like, what is it? I don't even see PowerPoint. PowerPoint only gets a tiny sliver of my computer's memory. Only a small percentage. Okay? So they all have to share nicely. And if you ever go outside of the amount of memory that has been given to you, you get a segmentation fault. So you try to access memory that's not yours or that doesn't exist in your inside of your system. Or if you try to dereference null, if you try to go to the null address and like get the value there, that's a special address that has been saved away that nobody can access. It's a nice default value. Okay, so that's a seg fault. Let me just make a nice program that seg faults quickly. Very easy one to make is this. segfault.cpp. So I'll make an int star p and have it hold the address that doesn't exist. I'll have it hold null. And then I'll try to say cout, hey, C++, please follow p. Give me the value at that address, at that 0 address that I'm never allowed to access. And so, segmentation fault, core dumped. Very scary error. But it's just saying that I tried to access memory that wasn't mine. And there's a million ways to do it. Try to access way past the end of an array, for example. That would give you a seg fault. That's not your memory anymore. It doesn't belong to your program. Are we good with that? Any questions about this idea of a segmentation fault? We've probably seen this before with arrays. But now you know what it really means. It's just saying that you're trying to access memory that's not yours. Does not belong to your program or is not writable by your program. Something like that. Okay. So 2 last examples. Let's do it. Pointers versus references. Let me show you the difference because they're very similar, right? So let's make a program that swaps the values of 2 variables, like we were doing before. First using references, and then using pointers, okay? So let's do it the way we know how first, and then we'll see how it needs to change to do it with pointers, okay? So this will be swap ref and address or pointer or whatever. So I need to make two variables, right? X equals 42, y equals 43, and then I'll make a swap by ref function. So I'll make swap by ref, and I'll call it with x and y, and hopefully they will have been swapped if I see out x space y. So let's make this swap by ref function. It's going to be void, it doesn't return anything, just does something for us, and it takes two swap by ref. It takes two ints, right? But we're going to take them by reference. So int reference, I'll call it A, int reference B. So the ampersand in a type means reference, not dereference, or not address of. So there's a lot to remember there. And yeah, remember how references work? They're just aliases for somebody else's int. So let's swap as we know how. Int temp equals A equals B equals temp. That should swap them. Let's swap by reference. And so I'm printing out 43 and then 42 because they got swapped. X is now 43, Y is now 42. So that is a review. Do we remember references still? In light of all the new things that ampersands can do. Okay, so let's make the same kind of function, but let's do it with pointers this time. But actually, let me draw what's happening. Let me draw what's happening again in the program. So main had x and y. They were set to 42 and 43. And then we called swap by ref, right? Swap by ref with x and y to be placed into the int reference A and the int reference B. So let me draw everything that belongs to swap by ref. Green, because I'm going to have to mark main's variables, as I've done before. This is swap ref, let's say. Swap ref, it has A and B, first of all, but they're references. They're just aliases for somebody else's variable. So A is going to be a reference to X, and B is going to be a reference to Y. So this is A, this is B inside of swap ref, right? And then it also makes temp. That's its own local variable inside the body. So it sets temp to A, that's 42. It sets A to B, so that makes it 43 here. And then it sets B to temp, so 42. Okay, so that's what swap ref is doing when it's running. Does that still make sense? That's how it's working. So aliases, we have the same name for a different variable, for somebody else's memory. We can touch it with a reference, just like that. Let me now swap stuff using pointers. So instead of swap by ref, let's do swap by pointer, swap by address, however you want to call it. Swap by pointer. And so I'm going to take an int star A. I'm going to take an int star B. All right? And if I want to call this function, I have to give the addresses of X and the addresses of Y. But first of all, int temp, that needs to be not A, that's an address. I need to get the address, or I need to get the value at that address. So I need to say star A, get the int. Star A equals star B. Star B equals temp. So that's just me manipulating pointers. Dereference A to get to what it's pointing to. Set these values, because this will be the X in main, this will be the Y in main. Star A and star B. That's how I'm going to use them. And then to call them, I have to say this. Swap by pointer. And I don't give X and Y. Again, I have to give their addresses. Int star A, that's an int star. That one's the address of an int variable, right? Address of an int variable. Star X and star Y. Okay? That's how that needs to work. And then we can print them out after it changes them. So this will also swap those values. So they'll be back to normal now. Now it'll be 42 and 43. Okay? Any questions about this code? I will draw another diagram though. But are there any questions immediately that you see? Like, does it make sense why this is doing what it's doing? It needs to take pointers this time, so ampersand X, ampersand Y for A and B. And then if I want to change the ints that they're pointing to, I have to dereference them. So it's got to be star A all over the place, star B all over the place. Temp is still an int though, that's still fine. Just needs to hold on to one of them. And the value is an integer still. So swap pointer will work like this. So now in main, before I called it, right, I had x set to 43 now, and y set to 42. And then I called swap by address, swap by pointer, swap pointer. And it doesn't use references, it uses pointers. So int star A and int star B, those are local variables. It has an A, its own A. It has its own B. They just hold the addresses of things. So A will be set to the address of X. So let's pretend that the address of X was 100, the address of Y was 104, something like that. Let's just make up addresses. So that means A will be set to that address of X. B will be set to that address of Y. So A will be set to 100. B will be set to 104. And so we have a pointer relationship going on now. A is pointing like that. B is pointing like this. Does that make sense? Those are pointers. And then again, we have temp. We say int temp equals star A. So here's temp. Temp equals star A. So follow A, get to the value. Give me the 43. Put that in temp. Then star A equals star B. So this value equals, follow B, this value. So we're changing X. Star A equals star B. So change this from what it was to whatever this value is, 42. And then we say star B equals temp. So star B goes here, going to manipulate this value. Star B equals what? This, 43. And so now they're back to normal. Any questions about the differences? They both are going to touch main's memory. We explicitly gave the address of places in main, memory that belong to main, to the swap function. And so secretly, that's what references are really doing. They're really just hooking all this stuff up for you, which is pretty nice. But yeah, this was the original version of how to do things. References are a C++ thing. Pointers existed at the very beginning of time, back when the C language was invented. All right. So if we're good with that, I just have one last slide, because something comes up when you have pointers to things, and then those things themselves are classes. So like a string, you make a pointer to a string, a pointer to a vector, something like that. Because you want to be able to do like dot size, right? S dot size, S dot at, all that kind of stuff. So let's see what needs to happen there. So let me make, call this, there's a special operator called the arrow operator. So if I'm going to use strings, let me include the string library, and so I'll make string S, ABCD. And then I'll make a pointer to a string. I can totally do that. String's a type. So string star SP, string pointer, equals the address of S. That's totally fine to do, right? Now, I might want to go through SP to get to the string and like say dot size on it, right? The one thing that won't work is like saying SP.size, right? Because that is not, first of all, let me just show you that that's going to not compile. Wait, what? Oh, sorry, I didn't try to print it. Excuse me. See how SP.size. You asked me for the member function size, but it's just a pointer, dude. So let me show you the problem here. If it's not apparent. So these two lines, they set up, of course, S, the string, and somehow it's holding on to ABCD. I won't pretend to tell you how. Let's just assume it's somehow stored there, and it lives at starting address 100 or something. Okay, that's where S is. Then I set SP to be a pointer to S. So SP is a box in memory that points to S, which means it holds the address of S. It must hold 100. And then I tried to say SP.size. It's like 100.size. That makes no sense. That's just a number. You can't use a dot on a number, right? It's the string itself that has a size method inside of it, right? There's the size. It's over here. I need to get to S before I say dot anything, right? That's what has the methods. So this won't work. Oops. That won't work. Won't work. SP is just a number. Da, da, da. So I need to get to the string before I say dot size. I can say s dot size, of course. How do I get to s from sp? Well, I have to dereference, right? I have to say star sp. That will then get me s, right? And then I can use the dot. Then I can say dot size. Does that make sense? I have to get to the string because it's the string that has the method. So that'll print the 4, as it should. Okay? Does that make sense? You have a pointer to a class. You need to get to that object to actually use its method. You can't just think that a number, the pointer, which is just a number, has the method attached to it too. No. You have to follow it. Everybody thought this was horrible. Like, the precedence rules require you to put these parentheses. You can't just say star sp dot size, sadly, because it would try to do this part first. So you're forced to use these parentheses, and everybody didn't like that. So back in the day, they came up with this operator. It's called the arrow operator. It's a dash and then a greater than sign. Looks like an arrow. And that is equivalent. It is the equivalent of first dereference sp and then use a dot on it. Okay? Combination of deref and dot. So I could equivalently say, or equivalently, I could say sp arrow size. That does the same thing. It's going to dereference and dot for me. And pretty much everybody prefers the arrow. Okay, so that'll also be 4. Does that make sense? So this is just shorthand for this, and this is necessary because we need to get to s to say dot size. And it's star sp that gets us s. Right? That's the s. And those are equivalent. Equivalent. Maybe I'll use 3 lines here. Equivalent. Just like that. So that's the arrow operator. That's when you have pointers to classes or structs. If you just want to get a field, you got to use that too. Dereference and dot or the arrow. Okay? Any questions about that? Or anything else we did today? Because that's where I want to stop. All right. So, let me just confirm. Yeah, so no new assignments this week. The next lab will be next week because that's when your current lab that's out is due.